Got it. Can everybody hear me okay? Yeah. Okay. So I'm going to talk today about X-ray emission from planetary nebulae. We touched a little bit on it early, and there's another talk coming up later on in the afternoon from Jesus that's going to touch on diffuse X-ray emission. I'm going to focus more on the central stars of planetary nebulae and the X-ray emission that we see from them, which is peculiar. This is work that's being done via the Chandra Plans survey, which is a Chandra Planetary Nebula survey. And an overview of this, we published the overview of this in 2012. It's under Kastner et al. And a lot of you in the audience are on that. This is what we're trying to do. This is the sun in the middle. We're trying to survey everything out to about 1.5 kiloparsecs. These are all the planetary nebula in that from the FRU catalog, with the circles representing the different sizes of those objects. The overview paper features all of these dark sources, and the bright purple sources are the new ones we're getting in cycle 14, which are rolling in now, and Marcus Freeman is spearheading the effort to reduce those at RIT, and myself as well, and Joel, of course. Alright, so here, this is what the sample looks like so far. This is the cumulative number of planetary nebula that are available in the volume limited sample of 1.5. This is what we have observed. And you can see we're not complete at all in any of these bins. We're about 50% in most. This is cumulative distribution as well with nebula radius. And you can see here we are actually mostly complete. We have the most compact objects. That's what we actually targeted in the cycle 14 cycle. Most of the most compact objects, which we expect to have most of the diffuse X-ray emission. So to remind you all, this is what you see in X-rays. That's off. That should be moved. But anyways, you see behind that arrow, trust me, there is a star, a point source X-ray emission. And then you see the diffuse gas as well. And the diffuse gas almost always resides within a nested optical bubble type shell that's usually really bright in O3. I'm sorry, a reminder to the first timers that this is actually caused by the interacting shocks between the winds. It's predicted by models, but the observations don't quite match with what we predict, but we have some ways that Jesus will talk about later on to bring those two together. The stars are not hot enough to actually emit X-rays, which is why they're peculiar, and this diagram here shows that all of these sources lined up with the characteristic energies of those point sources and diffuse sources as well, but all of them are on here. And what you see is that all of these stars, which are the points and the squares, all of the squares and points in this diagram do not at all behave like we expect a central star to behave. The only one on this diagram that behaves like a central star is a central star of M29. That's where a black body type distribution would lie. All the rest of these we have to try to figure out what's causing the X-ray emission. We also put this in our overview, which is the nebula radius here and the median energy, so the energetics of the X-ray emission. And what we find is that you see mostly diffuse sources, the triangles and the squares, at the very small nebular phases. And then as you get to larger radii, which is a proxy for H, you see less of that, and you start to see mostly just these point sources. And you see very energetic point sources up here and less energetic point sources down here. These are all binary systems. Two of these are close binary. That one has a very active spun-up giant companion. And so we think the X-rays are coming from the companion in all of these. Probably these two. We have no idea what's going on here. And then these I'll talk about in a little bit. This is an overview of the HR diagram and some evolutionary tracks, where the central stars lie, where all our detections lie, and where most of our non-detections lie, which are at the late stages of the, after they've turned over and they've gone heading towards the white dwarf cooling track. We stop seeing them. So, again, what are the possible explanations for this, for these X-ray emitting point sources? Wow, everything gets shifted. That's okay. two potential physical processes going on here. One is that we're looking at thermoplasmas. The other is that we're looking at a photosphere. Those are the two paradigms under which we can model these things. If it's a thermoplasma, there are a number of possible origins for the X-ray emission. It could be corona, either from the central star itself or from a companion. It could be wind shocks, like in O stars. If you have a self-shocking wind, you can create X-ray emission. Or it could be low-rate accretion back onto the white dwarf. In the photospheric case, it could be due to non-LTE effects. And so we're trying to figure out what's going on, but the main problem is that these four objects are the brightest central stars that we have the X-ray spectrum. So here's the energy down here and the count spike up here. And you can see that they all have very different shapes. M29 is here, it has no X-ray emission above 0.3 keV. There's no calibration down there. And so we have to make up our own. The Helix Nebula, you can see the black body distribution from the central star, and then you see this hard component that we're having difficulty figuring out what it is, but it looks like a 10 megakelvin plasma. All confined to the point source, no diffuse emission. And then Lotar 5, which is, we are pretty confident is coming from the companion to it. And then this is NGC 246, which has the hot star here, and then it has this feature here, which has been attributed to shot carbon. And this is what we actually have from all of the other objects, which is a very, very few counts, very, very limited number of counts, so it's really hard to actually fit these with spectral models, but nevertheless we tried. Down here I'm showing the temperature derived from the fit to the X-ray spectrum when I allow the column density, which is a crucial parameter, to be free. And over here, I'm showing the temperature when I use the Balmer decrement to convert to column density, freeze it to that value. And so they pretty much all lie here. The temperatures agree, except for maybe these here, but the error bars go into the range where they are happy. But the problem is really, if I try to fit everything, I get huge errors on my normalization. And those errors in normalization are going to lead to huge errors in the X-ray luminosities. And so we essentially are going to constrain almost nothing. This is what I mean. This is the NH from the X-ray spectra. This is the value from H beta. And you can see that when I let this value free, when I leave this value free, I get huge ranges of column densities. But in some cases, I get really good constraints. This is a plot of the fitness, but I'm going to just go on through this and show you essentially that what this plot is telling you is that these are the only ones that we can rely on for the spectral fits. The rest of these, any model can essentially fit the few data points that we have. Right, and you can see, I didn't tell you before because this is a big reveal, but there are actually two lines there, and you can't see them, but there are two spectral fits for all of these spectra here, and they look almost indistinguishable. So we're switching into another way to analyze these using a lot more of the characteristics of the photons using median energies. And in this case, we're looking at thermoplasmas, and we're looking at the effect of column on all of these. So this is a 1 megakelvin plasma, and as the column increases, you get less and less soft photons, and so the hardness appears to increase. And so we're going to try to use this to actually figure out what's happening. We do this by turning those into distributions and then just calculating what the median energy of that energy distribution is. And that's how we can turn the median energy into a proxy for the temperature of the plasma. We can do the same for the non-LTE models. These are the Rausch models, and this is 80 kilokelvin, this is 150 kilokelvin. This is typically for about a central star that has about 10 to the 3 solar luminosities. And you can see that you see the soft part, and it disappears as you increase the column density, but it's really only for these hot, bright ones that you can actually see some X-ray emission leaking into the hard energy spectrum, which is what we are seeing. We do the same thing for this, and you can see here what's happening. And this is all of that together in one plot. So column density on this side, median energy on the bottom. And this is where our sources, thank you. This is where our sources lie. The point sources are the central stars, the triangles are the diffuse sources. So I've separated these two and calculated the statistics on both of them. We know that triangles are coming from thermoplasmas. We know they're coming from thermoplasmas that are from 1 to 3 megakelvin, and that's what this all suggests they are doing. The point sources also seem to be coming from thermoplasmas in the same range. Some of them are hotter. These are hotter. These are about 10 megakelvin. And some of them are down here at about 0.3 keV. And that is M27, the only star that's behaving like a black body. Those are black body models, and this calculation is a little bit off. They should be shifted a little bit, but ignore that for now. This is what happens when you add the non-LTE models. So what happens, these hot stars, as you increase the column density, it gets rid of the soft, and they turn over into harder sources. But like I said, it's only about these three models here that are in the range of temperatures that we see from the central stars of planetary nebula. So we can't quite explain all of this as non-LTE. In fact, it's difficult to explain any of these as non-LTE because ultimately the spectral shape predicted by the non-LTE models does not match. But that could be an abundance problem. So, conclusions, but not really, because I have more. All of these up here seem to be the binary systems. These here all seem to be shocks, I would say. That's where I'm going out on a limb to say that these are shocks. And then non-LTE effects might be happening in these three down here. Why do I think those are shocks? Well, actually, maybe I'll touch on that. But I just want to touch on the Cycle 14 highlights that are brand new and that Marcus Freeman has on his poster. He'll be here today and tomorrow, I believe. And essentially we found point-like sources from these planetary nebulae. Some of these may look familiar to you, some of them may not, but you'll see them on Marcus' poster. And we've also found diffuse hot bubbles. Remember, in Cycle 14, we're targeting the most compact planetary nebula, so we're up against two things. We're looking mostly for diffuse emission, but we're also in a regime where there's a lot of circumstellar material, and it's easy to absorb those X-ray photons that we're trying to see. So I'm going to show you where these lie on this diagram. The dark points here, the black points, are the new observations, and you can see we have some really, really energetic sources over here, and we have some normal plasma-looking things here. Again, the triangles are the diffuse sources, and we have 4, and then we have 3-point sources. So far. So this is Hubble 5. This is the HST image. This is in the H alpha. And I have placed the green contours here onto the X-ray image to show you kind of what we're up against. Like we are looking at very, very few counts. If you look at this and I tell you there's a diffuse emission all over here, you're probably going to laugh at me. But I'll aid your eye with some screening. And now you can see clearly there's X-ray emission here, there's some X-ray emission here. Whether this is all coming from the star or whether this is background, it's going to take some more work to tease out. And it looks like there's another clump of emission here. But perhaps even more interesting is if we look at the core, if we look at this region here and zoom in. So the star I think is here because that's the brightest point, but maybe here, maybe obscured, it's hard to say. But the point is that the X-ray emission that we're seeing, which is just a few counts, but enough to be a solid detection, is all coming from this material here. So it seems to be some kind of new shock going into the material, or it's a reverse shock from the outflow of the material. It's hard to say what's going on there, but we definitely want to try to target this for a much longer observation. Right. I'll stop there, but essentially, if we could see chemical differences, then we might be able to figure out what's happening with these. If you change the carbon abundance, you really fill out this diagram. And so all those stars that are in between there could actually be explained by differences in abundances. Similarly for neon, if you change the neon, you just turn this grid of lines into a zoo, into a spaghetti mess. Thanks.
Time for one quick question. Yes, Martine.
Yeah, just a short remark. The central stars of origin planetary Nebulae,
they also emitting X-rays. We know about 30, and we just got Asymmetrical observation of level 78. There is some points of the central star. Origin, unknown.
Well, and interestingly, you indicates that it's probably maybe coming from shocks in the winds.
Okay,